So a quick public service announcement. So when you're running on the STOAT cluster, the Open Cloud cluster, the CMU Hadoop cluster, so that's a decent sized cluster. It's got a lot of worker machines. I think there's just one machine that's used as sort of like the login point. So when you log in, people are all on one machine, or maybe it's a handful that sort of get that share that job. But most of the cluster is not devoted to the login nodes. And the login nodes, so there are not very many login nodes compared to the some number of people that might be there. So it turns out that's actually a bad place to run a compute-intensive job locally, right? So if you do that, you're basically sort of like cutting off access to the cluster. So if you log into STOAT, then feel free to like run little kind of short, debug things if you're using like the tiny data sets. Certainly it's fine to sort of like debug things, but don't run any long, heavy processes on that node. So that's just a quick public service announcement. So today we're finally going to start talking about parallelizing the structured perceptron update. I want to start by just kind of whizzing through. We've covered a lot of different stuff over the last few days. Some of it's not really stuff that's kind of in the standard 601 courses. So we've talked about the perceptron algorithm, right? So this is this very simple online learning algorithm. So there's an adversary that's providing instances to a learner. So the learner gets an instance, and it has to make a prediction for each instance. And after it's made that prediction, it finds out if its prediction was right or wrong. So here these predictions are just +1 or -1. And the way you predict is by just taking the sign of the inner product of your instance and your weight vector. So a very simple learning algorithm. And then the update is also very simple. If you've made a mistake, you basically either add the last example or subtract the last example. And somewhat surprisingly, we can show that you get convergence if the adversary plays by a couple of rules. So basically, rule number one, and you can relax this, the delta trick kind of relaxes this, but rule number one is that the data has to be separable, and it has to be separable with some margin gamma, all right? And the separating hyperplane can't include really huge weights, so the norm of the separating hyperplane is 1. The examples also can't be too complex in the sense that their distance r squared from the origin. Okay, so in pictures, if we're looking at a two-dimensional space, this essentially means that you're sort of consistently labeling things positive in this behind this green arc and negative outside this behind this red arc. You're never giving examples that sort of exceed this radius bounds. You're never giving examples from way out here. All right, and you're never giving examples that are sort of right on the decision boundary. Everything's distant away from that boundary by at least gamma. Okay, so if that's true, then you can get this bound on the number of mistakes that get learned while this machine is in the process of making its predictions. So it's only going to make k mistakes. K is larger when this radius grows, and it's smaller when this margin grows. So if things are more easily separable, then basically k is smaller. Okay, so we talked about this. We talked about some extensions to the analysis, which show that you could actually get some mislabeled points. And you pay by sort of having more mistakes, but you don't have to change the algorithm. And then there were a bunch of more substantive changes, okay? So one were these ideas of voting and averaging perceptrons. So they have similar performance, at least in the simple case, but they're a little bit different, mathematically. So voting and averaging are both more expensive than a regular perceptron. People do averaging much more than they do voting, because voting seems to be sort of, irredeemable. It's just an expensive operation. But averaging you can make fast using this sparsification trick that I talked about. And then we talked about kernel perceptrons. And this is mostly kind of for background, and so I could present this view of the hashing trick as a kernel. Right? Then I talked about two other things, ranking perceptrons and structured perceptrons. So we've covered kind of a lot. I'm going to spend maybe 10 minutes just kind of doing a kind of quick refresher. So the voted perceptron is based on this simple idea. We look at all the hypotheses that the online learner has entertained during the course of its learning process, all right? And it turns out you can make some claims about a randomized algorithm. So the randomized algorithm is you pick one of these at random according to basically how many examples it was used for. So there's the weight for that is mk over m. So you pick one at random, then you predict using that, that hypothesis, okay? And in fact, there are two approximations to this that people use all the time. So so there's an analysis, basically, of a very simple analysis of the one where you choose and then predict with your choice. Another thing you can do is you can take a weighted vote. So you predict with all of them, right? And then rather than choosing one to make your prediction at random according to this weight, you look at all their predictions, you weight their predictions. So you're weighting a bunch of sign functions. And then you predict using the sign of that weighted vote. Another thing is a little bit simpler is you basically just take all the perceptrons, which are all hyperplanes, and you average them out using that weight, okay? So that's called the average perceptron. In a lot of settings, they perform very similarly experimentally. And the average perceptron is actually a pretty efficient algorithm. So the average perceptron is kind of one of these algorithms that, you know, if you were going to go on a desert island and you don't want to bring a lot of code, you're going to be there for a year or something, you would probably bring the average perceptron. It's a very simple algorithm, and it performs really well compared to its simplicity. So the regular perceptron, basically, the complexity is this, right? So if there are n non-zeros in your entire set of examples, you sweep through each example, and if there's a mistake, you might not have to do anything, right? But if there's a mistake, then you do an update, all right? So predicting, the prediction step, where you're computing the inner product of v and x, and the update step, where you're basically adding x to v, both only depend on the non-zero values in x. So this is a very efficient algorithm for tasks like documents where things are sparse. And you can get the same complexity for the average perceptron, which, if you recall, works a lot better. But you have to do a little bit of work to kind of get there. I think the algorithm that I eventually kind of showed you was this one. Conceptually, what's happening is that for every example, you're taking the current hypothesis and adding it to a running average, okay? And if you look at what you're actually adding, the current hypothesis is itself the sum of a whole bunch of other examples, right? It's all the examples that you've made mistakes on. So every time you make a mistake on an example, it's basically going to get thrown into this running sum, and it's going to be added to all the averages going forward, okay? So you can actually do this more efficiently if what you do is for this average, you basically update it just once with the number of times that example is going to be used in all the updates going forward. And that's a closed form thing. If you know the number of total examples in the stream, you can basically do the update like this. So it seems a little bit counterintuitive. You're sort of putting the most weight for the first few examples, and then you're getting progressively less weight for examples kind of further on in the process. If you want to think about this in terms of stochastic gradient descent, in stochastic gradient descent, we have a learning rate. But again, sort of if you look at the fine print of all the analyses, and in fact what people actually do, the fine print says you should sort of start out with a learning rate that's not too fast, and then make it slower and slower with each epoch, right? So again, in stochastic gradient descent, you're doing an update in roughly the same direction. You're using the non-zero values, and you're scaling the additive weight of those non-zero values by the degree to which you've made an error, right? By y minus p, sort of the local error of that example. And as you go further, you're going to be making that update less and less, and earlier on, you're going to be making it more and more. So you have roughly the same dynamics here. The analysis is all quite different. OK, so we spent some time with that. Then I talked about the kernel version. All right. So kernel algorithms tend to be relatively expensive, so you don't spend a lot of time on it in this particular class. The basic idea is actually really easy to explain in the perceptron case. So when we look at vk.xi, if we remember what vk is, it's basically the sum of all the examples that I've made mistakes on, right? And in that sum, each example either has a positive sign or a negative sign. So I could plug that definition of vk in and distribute, and then I get something like this, all right? So y basically would be this formula. And this actually has sort of an intuitive meaning. You're basically looking at sort of the positive exemplars and seeing how similar xi, the thing you're classifying, is to those positive exemplars, and then subtracting off its similarity to the negative exemplars, and you're predicting on with the sign of that, okay? So this is another way of thinking about the perceptron. So generally, it's probably a little bit more efficient to do this than to do that. But there's a nice extension of this. So we're looking at a similarity here where similarity is dot product, but we can plug in other types of similarities. So typically we define something that's called a kernel function. So dot product is the prototypical kernel function. And then this function this score becomes this sum of kernel similarities between xi and the positive and negative exemplars. But there are other variants of this of this kernel function that you can define. So typically, there are two ways of viewing this computation. One way of viewing it is you're doing an inner product with W, okay? And W is computed as the sum of these exemplars, right? The weighted sum of these exemplars. The other way you're viewing it is you've sort of distributed that. So you're looking at, the weighted sum of similarities to examples, all right? And in this formulation, you can sort of plug in a different kernel function. So many of the kernel functions that we use, and maybe all of them, I guess we can say all the kernel functions we use, could be defined as basically taking x and transforming it and doing an inner product in that transformed space. So sometimes the transformed space is really huge, and there's some shortcut for computing similarities without actually doing that explicit transformation. So this gives you basically sort of two ways of doing this computation. You can do it based on the similarities, if that's more efficient, or you can do it with the transformed data, if that turns out to be more efficient, and then sort of explicitly keep a weight. So the main reason I spent a little bit of time talking about this is because we've actually done something like this, or we're doing something like this right now. So if you look at the hash trick, what we're doing is we're taking our hash table representation of an example x, right? And we're replacing this with this array, all right? This is actually a transformation of the data, all right? And this is like the transformation when we go from x to phi of x in using a kernel function, all right? And that's something that Mr. Langford and Mr. Smolla and their colleagues talked about sort of explicitly in the paper I talked about on Tuesday. So this is kind of an aside, but it gives you a little bit of insight into the way the hash trick works and doesn't break things. So then the last thing was I basically played some games by sort of building up more complex algorithms based on this framework. So the first one is one that we're not going to explicitly use in this class. So you can use these voted perceptrons for ranking as well. So here the API is, instead of giving you one instance to score as positive or negative, I give you a bunch of answers and tell you to give the best one. So these are like the SAT things where, someone says, well, what's the best analogy, right? Or which word is, closest to opposite in meaning of such and such, and it gives you a bunch of answers, and you have to just, there's one answer that you want to give. You have to choose out which one is sort of the best match to what the person has said. So it's not a true-false question. It's like sort of multiple choice, and you're choosing whichever one is best. Okay. So what B returns is the index of the one which is best. So it checks off one of those answers, proposed answers, and it does that by basically scoring them with inner product to its weight vector. All right, and then it gets the correct answer, and the update is almost the same as what we had before. You add the positive example and you subtract the negative example. So the negative example is what you guess, which is wrong. The positive example is what the correct answer is. And of course, if you guessed right, there's no update because those things are the same, so it's, the whole sum goes to 0. And we basically have the same sort of rules. The examples are kind of within a kind of sphere centered around the origin. And there's something, and things are separable, which means the best thing is clearly better than the second best thing, right? So we don't have any sort of near ties in this list. And here's a picture of this. We have a bunch of these x's are points, right? So the dot product with the true weight vector, visually it's just projecting those points onto that vector, okay? And this best one, which is in a green circle, is at least gamma away from the next best one, all right? And if we had another guess, a different guess, like say we thought this was the weight vector instead of u, so we're way, way off, then we would do a similar sort of thing. We'd project onto that weight vector. We pick the one that is furthest, which would be the circled purple one, right? And then our update, we basically subtract the thing that we guessed that turned out to be wrong, so that's the negative example, and we'd add the thing which is right that we didn't guess, all right? And that would kind of take us to a new weight vector up here, all right? So in this case, that's a lot closer, and in general, you can prove a very similar result, okay? You can show that you're basically getting, again, a bounded number of mistakes. It depends on R over gamma. There's a factor of 2, but other than that, it's essentially the same. So this is nice in a couple of ways. So both of these don't really depend on the dimension of the x's. So in principle, this algorithm should work as long as you have a good separation between positive and negative classes. There's no curse of dimensionality in this math, okay? The other thing that's nice about the ranking proof is it really just depends on gamma and where these examples are. It doesn't have to be a multiple choice with only like 4 answers per round, right? It could be a multiple choice over, a billion answers, right? So you could be a search engine returning the best page for a query, right? And even though the number of things you might have to rank is really huge, if you can do that ranking and get the answer quickly, we should still converge. So we should still learn quickly, make a small number of mistakes. So it doesn't depend on the number of things being ranked. So that's kind of an interesting observation. And this clever guy named Mike Collins figured out how to use that to force this ranking machinery to solve what seems at first to be a very different task. So in ranking, you get a set of things, you score them, and you return the best one. All right. There's another task called structured classification. A typical example would be something like named entity recognition or part of speech tagging. I have a list of words, and then I'm going to output a label for every word. But those labels are all correlated, and I want to sort of take into account the correlations. So really, the way we're going to think of this is a classification problem, but instead of just having, let's say, let's say 40 labels for each word, if we're doing part of speech tagging, I have 40 labels for each position in the sentence. All right. So if the sentence is, let's say, 20 words long, it's 40 to the 20. So I have an enormous number of possible classes. So it's just classification learning, but there are a lot of different classes. Okay. Is there a question? So there's a way we can sort of use this ranking strategy to do the same sort of trick. So I send you the word sequence, and what you're really ranking is you're ranking pairs, where the pair is the word sequence and the label, where the label is from this huge set. Okay? So you find the single best vector of labels, all right? Maybe there's 40 to the 20 of those, but you still have an efficient way of finding the best labeling for that sequence, all right? And then I tell you which one is actually best, all right? So we're basically ranking these pairs where we've got a word vector and a set of proposed labels, all right? This is basically a way of solving, using this ranking machinery for this API, okay? So all I basically need to do is be able to come up with the best labeling. And it turns out there are a bunch of cases where this is possible. I sort of suggested one of them. There's a whole class in LTI. I used to teach it, and then Noah Smith and Chris Dyer taught it for a while. I'm not sure if it's still on the book, so I'm not sure it's been taught for a while, called structured prediction. One way of thinking about it is what we're going to do is we're going to constrain all the features that we're going to use. So the features are basically properties of two adjacent labels, right, and the input, okay? So we could think, and then when we score those features, essentially we have a score of the compatibility of two adjacent labels relative to this input. So basically each set of features, or let's say all the features that fire, can be grouped into this sort of graph structure, okay? So here the labels are B, I, and O, begin inside and outside a name. I've sort of colored these things by, let's say, the weight of the features after you weight them with your current hyperplane. So once the hyperplane is fixed, I can basically do a shortest path algorithm and figure out what is the optimal sequence labeling, all right? And I can do that efficiently. So even though there are many, many different possible combinations, I can find the path that gives me the best label efficiently. I can also, if you tell me what the right labeling is, if I tell you the right labeling is, 0, 0, begin, inside, outside, outside, outside is the correct labeling, right? You can also look at all the features that fire along this path, all right? So since the features are local to like a particular pair of things, you can do that computation quickly. So this basically gives you a way of doing this voted perceptron algorithm for named entity recognition. So, in principle, we're, mathematically, we're ranking these pairs where each pair is a feature vector, a word vector, a sequence of words, and a label sequence, right? But in practice, all I have to send, I don't have to send this long sequence of possible candidates. I just have to send you the original word vector X, right? You never generate all those. You just tell me what you think the best one is by finding the shortest path or the highest weight path, right? And then I tell you what the right one is. So all the information that gets sent back and forth is actually small. Again, this expensive-looking operation of finding the optimal pair is something you can do efficiently. Okay, so the update's all the same, and you can basically make similar tricks. So this is nice because this gives us a very flexible way of learning. So all you really need to do is, given some X, you have to find the best label Y. That could be a complicated task, all right? You have to find the best label Y given an example relative to the weights. But the weights can be used in some sort of search or some non-trivial computation. So most of the time, in the math, you assume that you've actually gotten the single best thing. Experimentally, it often works if that search is approximate. So this is a nice trick. It's a nice trick to sort of have up your sleeve. So that's the end of my recap. Are there questions? Okay, cool. So on Tuesday, you guys did not have a quiz because it was like Jewish New Year. So now the New Year has started, so there's a quiz. Okay, 1 day off. Okay, and the quiz, I'm sad to say, actually does cover some of the stuff that I just covered in my recap, but that's so be it. Okay, so now we finally want to talk about taking this and parallelizing it and speeding it up. All right. So this is this nice paper by some guys who we're at Google. I guess Gideon is now at Bloomberg. I'm not sure where Keith Hall is now. So they were speeding up this structured perceptron algorithm. So they were using structured perceptron to give the best named entity tags, and then they had another task, a parsing task, where once again, given the weights, you can find the best parse using a CKY parser. But there's some dynamic programming search involved. So it's the same algorithm, sort of a different search routine involved. So this is sort of a nice task to think about when you're speeding things up. Does anyone want to guess as to why it's nice to look at these kind of structured prediction tasks rather than, say, like a kind of simple classification task when you're looking at speeding things up? So the thing that's different in this task is that you're doing some sort of search, right? Associated with, when you're doing the prediction, you're not just doing a kind of simple, mathematical operation, just doing an inner product. Instead, you're doing that inner product, but you're also running some algorithm, right? A Viterbi algorithm or a parsing algorithm. So how does that sort of change the mechanics of what's going on, or the trade-offs involved in computation? So when you're parallelizing the search, you're cutting off computation. Is that what you said?
Yes.
Yeah, right. I mean, in general, there's sort of two things you have to worry about when you're doing this learning, right? There's maintaining the parameter vectors. And in general, when you parallelize things, that can be a problem because the parameter vectors will get duplicated across the different things in the cluster, right? So they may get out of sync. So there's extra work involved in maintaining the parallel versions of the parameter vectors, all right? The other thing you're doing is you're actually doing classification, and you're doing a lot of classification. And in structured prediction, that classification could actually be somewhat expensive, right? So if you're doing an expensive step, so the classification is something that's easy to parallelize, right? If the game here was to basically just parallelize the process of making predictions, right, on a big data set, we totally know how to do it. We just distribute the weight vector and make all the predictions on the different data charts separately, right? There's no interaction at all. So that's like embarrassingly simple to do, right? So the prediction part is something we can parallelize easily. It's the parameter update and parameter sharing, which is kind of hard. So here you're spending more time on prediction, right, proportionally, and less time on parameter updates. So this is sort of a nice opportunity to look at throwing a lot of machines at the problem. So they look at a couple of approaches. So one approach is the simplest thing you can imagine. So the simplest thing you can imagine is basically take your data. If you've got 100 worker machines, split into 100 shards randomly, right? Then learn 100 different classifiers, on each of these different 1% of the data, okay? And now I've got 100 different classifiers, and well, we're doing maybe an average perceptron anyway, so at the end of the day, let's average those perceptrons that have been learned on these different fragments of the data, okay? So that's the simplest thing you can do, which they call parameter mixing. The flow looks like this. You just basically take your instances, you run a perceptron locally, maybe loop over that data many times until you converge. Then you take the weight vectors that you've learned in each of one of your parallel shards and you average them. Okay? So it turns out that doesn't work super well in the experiments. You can come up with counterexamples where you converge locally on these different shards, but you don't come up with a final, but after you do the averaging step, you no longer have something that classifies the data accurately. So it might be that at the end of the day, you haven't even really fit the training data well by the result that you get after this averaging step, okay? So that's the simplest idea, and they argue and kind of show experimentally it doesn't work that great. All right, so here's the slightly more complicated way. So what we're going to do is we're going to do the same sort of process, split the data into k different pieces, one for each worker. Then we're going to run each worker, but not until it converges. We're just going to run it through the data one time. Okay, so we'll make one pass over the data, and then we take all the hyperplanes, all the classifiers that are learned, take them and average them out. Okay, and then we redistribute that averaged weight vector to all the workers, and then we do it again. All right, so we're sort of alternating between, and then we repeat that process. So we're alternating between each worker taking an average hyperplane that's sort of been shared by all the workers and sort of is influenced by all the data in the whole data set. All right, and taking that hyperplane and adjusting it to fit the data that it sees locally. All right, and also redistributing the hyperplanes to all the different machines. Okay, so you're doing basically these two things. So for each worker machine, you're making one pass over the data, all right, which is just the usual perceptron algorithm, and then you average things out. And uniform averaging works fine in these cases. There are things you can think of that are fancier. So it would be plausible to basically do the same thing you do in an average perceptron, where you average everything according to how long it was active or how many mistakes it made, and they looked at some variance, but uniform averaging is really about the same. So this is the algorithm. We'll kind of come back to this step a little bit. So how do you take all those weight vectors and then average them and then redistribute them? Okay, so this is certainly something you can do in sort of a map-reduce framework. But if you want to think about how to do that without having any bottleneck machines, right, so that sort of the maximum number of machines are involved and workers are involved in this distributing the weight vectors, then there's some tricks you could do. So there's an operation called all reduce, which is used in settings like this. So it's commonly used in these kind of iterative machine learning algorithms. And here's a picture of that. Okay, so we have the weight vector. It starts out as all zeros. We distribute it to everybody. They run one pass through. We average the weight vectors. Okay, and then we send it back and redistribute it again. Okay, and then we repeat. And we do that some fixed number of rounds. Okay, so this is the algorithm. And what I'm going to do is I'm going to sort of do two things. I'll step through their theorem, their results. Then I'll talk about their experiments a little bit and sort of how far this goes toward solving things. Then I'm going to spend a few minutes talking about, the somewhat more general case. So that's the plan for the next 45 minutes, something like that. Okay, so here's the theorem. This is one more perceptron theorem. We're using their same notation, R's and gammas. This is basically what they claim. Okay, so S is the number of shards. That's the number of worker machines. N is the number of iterations, right? So you're running this iterative parameter mixing algorithm n times, right? So this is the number of times you go around that outer loop. Okay, and what they're claiming is something about the total number of mistakes that get made. Okay, so the total number of mistakes that get made. Well, we've got some notation here. So k of I comma n is the mistakes on shard I during the nth iteration of the outer loop. Okay, and these mu's are basically the weighting factor when you do the weighted average. So their results hold for many different weighting schemes, but this is just a weighting factor. Okay, so this basically says if you look at the weighted sum of mistakes made by each machine, by every machine in all the epochs, it's bounded. Okay, and it's bounded by R squared over gamma squared. Okay, which is the same bound you'd get for the regular perceptron, right? So that's the same number we'd get if we looked at mistakes for the regular perceptron. So as an example, you can say, well, supposing this is weighted uniformly. So this mu is basically 1 over s, all right? Okay, then essentially it says we have a bound on the number of mistakes that get made, okay? So this is basically saying that this iterative parameter mixing algorithm does converge. So I put a bound on the number of mistakes it's going to make. If the data is all separable, it will get there, which is not the case for the first, baseline algorithm where you just split the data and run the pieces separately. Okay, so we're kind of balancing the amount of work each processor does without getting new parameter vectors. So they're not exchanging the parameter vectors all the time, just like once per iteration. But that's okay. It's sort of enough communication to guarantee convergence. Okay, so if we think about all these mu's as just being 1 over s, so everything gets averaged out, all right, then we can actually write this out a little bit more clearly, right? So these are all 1 over s. So if I multiply this through by s, we can see what this number is. So this is now all the mistakes that are made on all the shards and all the iterations. Okay, so this is bounded, right? Like I said, it's bounded. You can see the bound has another factor of s. Okay, so some people are kind of looking at it and say, whoa, is that really a very good bound or not? Right, because essentially what I've said is, okay, I'm doing all my prediction. I've got this like Hadoop process in a big fancy cluster. So I can do it 100 times faster and I can still converge, okay, where 100 is the number of shards. But it's like, it might converge 100 times slower, okay? So you're using 100 times machines, the number of machines, and your upper bound is basically sort of the same as if you used one machine, right? So this is actually formally kind of a weak result. So in principle, we could lose all the speed up we get from parallelizing, okay, because the process converges a lot slower, all right? So this is the result they got. This is the formal result they got. It's not very tight, okay? And this is something that is kind of a general problem when we think about parallelizing learning algorithms. It's hard to do analysis that's sufficiently detailed enough to tell you how much you're going to gain. So before I do more math, right, here's the experimental results. So you can see what's actually happening here. So, so the x-axis here is wall clock time, and the y-axis is the accuracy. Okay. So one baseline is you just basically just run one perceptron on one machine. All right. Okay. As you run it, it's going to improve in accuracy more and more, and that's one perceptron. So that's those black lines right here. The average perceptron, you can see that actually performs better. All right. Okay. Then here's another baseline. You just do one perceptron, and you just run it on one shard. Okay. So of course that's really fast, but it's not going to do that well. So you can sort of see that's where it ends up. Okay. So these blue triangles are the first baseline. You basically split it, and then you average it. All right, so that's better than just taking one thing, okay? In this case, it's not as good as running that one thing on all the data. And in this case, it's way worse than running that one thing on all the data. So this, it's a better idea if you're, it's a good idea if you're in a big hurry and you don't have that much time to wait for your classifier. It's a bad idea if you want a really good classifier, okay? And then this iterative parameter mixing is this top line with the light blue diamonds. So what we can see is it basically, it's converging faster and getting to a better result than the other baseline results. And this one with the average perceptron is really the one we care about. That's where the numbers are highest. All right. So this is for named entity recognition. So experimentally, it looks like this is helping quite a bit, right? You're getting to a good place much faster than you would have in any kind of the other kind of baseline settings. This is for parsing. So again, these blue triangles are the result with their iterative parameter mixing algorithm. This is just a single serial perceptron, which gets there eventually. Okay, and this is just taking just one shard of the data. And they don't have the non-iterative parameter mixing for this result for this case. All right. So this is experimentally what's happening. It seems to work pretty well. So let's look at the analysis, because the analysis is actually not all that complicated, particularly now that we sort of have gotten perceptrons in our head a little bit. So this is the claim they're going to make. So a little bit of notation here. W average n is the result you get from averaging the nth iteration. So it's the final weight for shard I in case n, and then they're all averaged out by these mixing weights, which we can assume just be 1 over s. All right. So they make two claims, which are basically just kind of exactly the claims that you see in the perceptron analysis. So one is about the dot product between u and this w of I of n. All right. So basically, what we saw before is that you basically, that this dot product increased by at least gamma with every mistake. All right. So here what we're basically showing is that this increases with every mistake that's made by the ith worker on epoch n. Okay. Right? So it's increasing by gamma, and the start point here is just the average at point n minus 1. All right? So we could kind of step through these intermediate points, but that's basically exactly the same analysis that we used for the ranking perceptron a few slides back, or on Tuesday, right? We're basically plugging in this definition, okay? So we're saying, well, this is what happened at point n minus 1, okay? Right? So if we look like one step back, one mistake back, we can see that this is we had this weight vector, and we can this is the result after the update, okay? And then again we can basically turn that into a gamma, and then we can sort of kind of push it forward and show that there's an update of gamma at each step. All right. So this is basically exactly the same observation we had before. It's just kind of translated from a weight vector, which corresponds to mistake k minus 1 to mistake k. So this weight vector, which is the last average point, okay? And then we're updating, and then the number of gammas we sort of add onto that is the number of mistakes we make in that shard. All right. So this isn't surprising. There's another one which is also not surprising, which is basically that the size of that weight vector also grows by the number of mistakes times r squared. Okay, that's again just the same analysis we had, right? Whenever we update something, we're adding it by basically the difference of two examples, so that's fine. Okay, so they call these observations A1 and A2. Okay, and this is just the standard perceptron analysis. Okay, nothing's new. All right. Now they want to make these complicated claims, all right, or more complicated claims. So this is using mathematical induction. So they have this hypothesis here, okay. So for all n, this statement holds, okay. And then for all n, this statement holds. So this is about how much you converge in terms of inner product similarity. This is how that basically bounds the size of the weight vectors in terms of r squared, okay? So let's look at this, all right, and let's look at proving this first one here, which is kind of a little bit more interesting. So here's the base case, okay? So the base case, we want to see whether that's true for n equals 1, all right? So for n equals 1, this is just a sum from 1 to 1, okay? So we can rewrite this as basically saying this, okay? Right, so the number of, so if we weight these things, and we look at that inner product, that's what the claim is saying. So I want to verify. So this is basically just the definition of what that what this quantity is, right? And we want to verify that this is true. Okay. So we've never really thought about this before. So we've never really thought about what these averaging operations might do. So this is actually, there's something to kind of say here. all right? But it actually follows pretty directly, right? So we know that this UWI1 grows as the dot product. It's bounded by this UW0, the first, the 0th iteration. So that's the 0 vector, okay, plus K gamma, right? So this dot product we can immediately bound, and that gives us this result, okay? So this basically shows that this claim is true for n equals 1, okay? So we have this claim for n equals 1. Now we want to show that, given some particular value of n, I can prove that it will hold for the next value of n, all right? So the inductive case, I'm allowed to assume it's true for n minus 1, and I want to prove that it's true for n, okay? So this is what the average weight vector is, okay? It's the average of the weight vectors for each shard, okay? So this first step here, what are we going to do? We're going to take this quantity here, UWIN, and we're going to place it with the previous average plus the number of mistakes, okay? So that's actually the first thing we showed. That's the statement A1. So this is basically our old perceptron analysis, basically showing something about how much this quantity increases, the similarity increases within a particular shard. Okay, so that's the first step. Okay. In the second step, what we can basically do is I'm sorry, this is in the original paper, they left out that gamma. So this is all just from A1, okay? It's from that bound we had a couple slides back. Now I'm going to take this quantity and we'll distribute these, this sum over these two different parts. So I've got this part and I've got this part, okay? So this part just kind of gets copied over, okay? This part, I guess I should have like a sum of s from 1 to I from 1 to s of, mu I times this quantity, right? But we know that this sum is 1 because it's a distribution, okay? So we're basically taking a sum over all the elements of a distribution of something which is a constant with respect to that distribution. So I just end up with that constant. All right, so this is now, this part, it kind of goes away on this part, and we still have it here, okay? So now the next thing to do is regroup, okay? We're basically done, all right? We're just going to regroup. So this quantity here, it's just that sum from, n minus 1 to s, right? And I know from my inductive hypothesis that that's greater than this, okay? And then I just carried this over here, okay? And now I'm basically done because this is basically the quantity that I have right here, okay? So that's the claim I want to make, all right? So this quantity here is the only one that's even slightly mysterious. And again, what we've really done is we've taken this sum and we've distributed it across this big sigma sum, right? So we end up with the sigma sum for I equals 1 to s of this leftmost quantity here, and then the sigma sum from I equals 1 to s of this rightmost quantity. And since that's a distribution, we can kind of get rid of it, all right? That gives us this, and then we basically just regroup, okay? All right, okay, so this is using the inductive hypothesis right here to get this quantity, okay? This is the inductive hypothesis, we believe it's true for n minus 1, right? So if we sort of plug in that value for n minus 1, we'll get this. Okay, so that's the first one of these, okay? I'm going to be really nice and not show you the proof for the second one. It's really pretty much exactly the same. There are no new tricks in it, right? It's basically just taking these same observations, doing the same manipulations. And together, those pretty much directly imply this bound, okay? So this is basically the analysis they do, all right? So now let's go back to what this is actually saying. So the question is, could we lose our speed up from parallelizing and lose it to slower convergence, all right? Now, I showed you some nice experiments for a particular number of shards, right, that showed you could get an improvement. Here's some experiments where they basically look at convergence rates. So we know the best one is the iterative parameter mixing, all right? And here's what happens when you do 10 shards, and here's what happens when you do 100 shards, okay? So now, of course, when you do 100 shards, each epoch is going to be 10 times faster, okay? So the number we have here is training epochs, not wall clock time. So that's important to realize, okay? But I guess, so this is actually showing you two things. They're showing you uniform mixing and mixing based on error rate, which are, you know, basically indistinguishable. But the big thing to notice is that as you get more parallelization, as you go from 10 to 100, right, you are in fact seeing slower learning rates, all right? So this isn't just an artifact of the analysis, it's something real, all right? So, and again, what's happening here is that each one of the workers is basically getting a much more local view of the data. It's only seeing 1% of the data instead of 10% of the data, okay? So you need more time for the information about the rest of the data set to sort of percolate through the whole system intuitively, okay? So this is a real problem, okay? And they actually have a nice discussion of this here, okay? So they basically say, in the worst case, convergence can be proportional to the number of shards. So there's a trade-off between slower convergence and faster epochs, because the more shards you have, the faster each pass is, because each, you know, if you have 100 shards, they're only doing 10% as much data than if you have 10 shards, right? Okay, so they saw a tipping point in their experiments where increasing the number of shards actually slowed things down, okay? For the named entity experiments, it's around 25 or 50 shards. So you can get a speed up of 50, it's not nothing, okay? But you can't get a speed up of 500, right, or 1,000, even if you have 1,000 worker machines, which they certainly did, okay? And then they say this is sort of due to a couple of different things. So one thing is, as you get more and more weight vectors, and even with like 1% of the data, the final weight vector you get at the end of the pass is going to be a dense vector with lots of non-zero parameters, okay? So you're spending a lot of time moving these big dense vectors around from machine to machine. So there's overhead in doing this synchronization. Okay. And this is, I think, that's something that's generally true. There's a trade-off between increasing the training times, okay, and slower convergence. All right. So are there questions about this? So this is one particular analysis of one particular algorithm, all right? And one reason I do it is because the analysis does sort of matter. This analysis isn't too hard to do. You know, it doesn't, you know, require a lot of complicated measure theory or anything like that. The other thing is that this particular algorithm gets used all the time. So iterative parameter mixing is sort of the obvious way of doing iterative machine learning on a cluster environment, right? If you've got a cluster, that basically means your workers are not that tightly connected. There's a high communications cost. So what you want to do is you want to do a lot of computation, a lot of learning locally before you think about synchronizing the workers. All right. So IPM in a Hadoop-like cluster, iterative parameter mixing, is the natural way of doing things, and it's been used over and over again over the last 5 or 6 years for lots of different problems. So people use it for LDA estimation and stochastic gradient descent type things and so on and so forth. So this is a very common approach to distributing machine learning algorithms, and you often get a similar sort of effect. You often get a trade-off. A little bit of parallelism is going to speed things up, and then you're running into the point where the parallelism is interfering with the learning rates. Okay, so the fact that each machine is only seeing a little bit of data before it has to synchronize means that you're actually spending more time than you want to. So essentially at some point the communication costs start dominating the actual computation costs that are involved in updating the parameters and the real learning. Okay, so this is coming up. This is a new part of the lecture. I haven't done this before, so this is all kind of new for me. All right, so it'll be new for you. What I want to do is I want to spend a little bit of time talking about how these techniques, how these analytic techniques have been extended. So another reason why I like the perceptron thing is because this kind of incremental bound on your progress, the mistake bound, is something that's used a lot in mathematical analysis of learning algorithms, particularly parallel learning algorithms. So there's this famous paper called Slow Learners Are Fast, okay, or from around the same time. And they were looking at essentially the same sort of question, right? So if I have multiple learners, if I want to parallelize my learning process, how can I do it, right? So what they did mathematically was a little bit different. So I guess the first thing is they weren't just trying to talk about perceptrons. They were talking about a much more general machine learning setting, okay? So they were talking about doing this for an arbitrary stochastic gradient algorithm. In fact, they were doing it for more than a stochastic gradient algorithm. So their algorithm is the following. So essentially, you take a gradient step. So their notation is this, okay? They're treating this learning task. I mean, they're really interested in learning, but they're treating this as an arbitrary optimization problem, okay? So F here, okay? The thing you're optimizing is the loss function, okay? All right? And ft is the specific loss that you got on the teeth example, okay? The x's here are what were my w's before, or my v's, okay? So these are the weight vectors. These are the parameters on which the loss function depends, okay? All right, and gt is the gradient, okay? The gradient of those parameters at the teeth step, okay? So this would be the update you do in the stochastic gradient descent, all right? So the algorithm is basically, they go through this process, okay? Forget these taus for a second. They go through this process, okay? And at each time step, you incur loss ft, all right? So that's the loss you got for that example, all right? So in our analysis, we're going to talk about how much loss we've incurred, all right? So if this was stochastic gradient descent for logistic regression, that loss would be something like a conditional log likelihood. So you'd be looking at, basically that loss summed up over all your examples, all right? So it's analogous to, but it's a generalization of the notion of mistakes we used in the perceptron case, all right? Then we look at the gradient of that and we do an update, okay? So what's their update? So their update is also a little bit more general than we've talked about before. So in stochastic gradient descent, we just look at the gradient, we take a step in that direction, and we're done. In other learning settings, there might be some constraints on what the weight vector should look like. So for example, instead of putting a penalty on large weights, I could just say, well, I want the weight vector to be no more than norm 1, right? Or I could say I want all the weights to be non-negative. Or I could say the weights all have to be in a simplex, so it's a probability distribution. So it could be that there's some constraint on what those weights should be. So in that case, what you do is something called projected gradient descent, okay, right? So if there's some subspace, like the positive parameters, that your weight vectors have to stay in, then what you do is you take a gradient step, and then you find the closest thing in your kind of valid space of parameters. That's a projection step. Okay, so in their analysis, they talk about a projection step. That's what's going on with all this notation here, right? So this basically means take the closest thing in X, your set of legal parameter values, all right, to the place that the gradient is taking you. All right, so xt minus, eta t gt, okay, is where the gradient's taking you, okay? All right, so this is their kind of generalized projected stochastic gradient descent, all pretty kind of standard stuff if you like look at this stuff all the time. And the thing they're doing new here, okay, that kind of the big contribution of this is they're looking at not the gradient at time t, but the gradient at time t minus tau. Okay, so tau is basically a parameter that tells you how stale your parameters are, or your gradient is, right? So what you've done is you've actually taken the gradient not with respect to your current parameters, but with some old parameters, okay? So why does that kind of make sense? So imagine we've got a bunch of, processes, like, in the iterative parameter mixing. They're taking gradient steps, all right? And they're updating their parameters, and every once in a while they sort of stop and synchronize, okay? So what does that basically mean? That means that there have been a bunch of, so since the last time you, worker one, looked at an example, the gradient's been updated by a bunch of other workers. So conceptually, there's one gradient you all should be sharing after every update, okay? But you do one gradient step, and then the other 10 workers have all made gradient steps. So there's like 9 other gradient steps that you don't know about. So conceptually, what you should be doing is using the gradient of, the parameters after all those updates. But in fact, the one you've got is now 9 updates old, right? So we're going to see what happens if we took a gradient that was right with respect to an old version of the parameter vector, right? So this is to model the fact that you have multiple learners that are kind of getting a little bit out of sync. So iterative parameter mixing is one way they can get out of sync, but there could be other ways, right? You could imagine other processes where you got different parallel learners that are communicating in some other way. So this is the mathematical process, okay? And what they're analyzing here is basically how, this is the analog again of mistakes. So in mistakes, we basically look at a case where the data is separable. So if you knew what the right hyperplane was, you wouldn't have to make any mistakes, okay? And I charge you for the number of mistakes you actually made in the process of learning those parameters, okay? So here what we're looking at is a similar sort of thing. We're looking at the loss you actually did incur, that's this guy, versus the loss you would have incurred with the best possible set of parameter vectors, okay? So XR is the best possible parameters that you could have. So in the case the data is separable and you're using, an error type bound, that would be 0, okay? So it's just like sort of the number of mistakes you make, okay? In the case the data is not separable, it's basically the number of extra mistakes you could make relative to the sort of optimal hyperplane, okay? So this is basically our measure of how good we're doing, okay? If this is small, that's good. Okay, if this is large, that's not so good, all right? So what we're trying to do is we're trying to bound this, okay? So here's some of the results that they have in the paper, and I'm not going to go through them in like sort of like the kind of theorem level, but just at the result level, okay? So there are a couple of things that we're looking at here. So t is the time, so it's the number of examples you're looking at, okay? Tau is the staleness, okay? And there are a couple of other numbers here. So if you have a gradient that's really sharp, okay? So yeah, at some point, your learner is going to have to make like a really kind of like dramatic correction in response to some error. Then you'd think it would be harder to do this kind of online learning. So you could kind of go for a ways before you have to make a like really big correction. And that kind of like shows up here, right? So L is basically a bound on how big the gradient can be at any point, all right? Another thing that can affect things is basically, and I guess this is related to the size of the separating hyperplane in the perceptron analysis. So if that hyperplane has really large weights, then this could be a gradient with that hyperplane could be larger, okay? The other thing is there's some notion about radius, okay? So what's the radius here? So here the radius is basically this quantity right here. So we're looking at the distance between two examples, and this is the square of the two norms. So, this would be the kind of inner product of that distance with itself. All right, and we're basically seeing how large that gets. Okay, so f squared is kind of the quantity that bounds that, right? So this quantity f here is kind of like our radius quantity. So if the radius is small and the gradients of the examples are of the loss function is bounded, this could also be unbounded if you have like a really large loss at some point. Okay, and the gradient of the loss is bounded, then we get this result. Okay, so this is actually kind of a nice result. So the kind of a normal result you get normally if there was no staleness is roughly like this without the tau in there. Okay, so this makes it look like tau is getting making things slower by about a factor of the square root of tau. Here's another result they have. If you change the rules of the game so that each worker basically is only, so this is a particular algorithm, okay, right, where tau is a parameter that tells you how stale it is, right? There are lots of other algorithms you can imagine, right, that might work and might give you bounds kind of like this, or maybe even better, who knows, right? So another question is, this tells you how well this algorithm works, and it's not terrible, okay, but it is slower, right? So what if you had any algorithm, and the only real constraint is basically when it's doing its update, it can't look at any information from the last tau time steps, all right? So there's a lemma that basically says if you're constrained to look at information from at least tau time steps ago, all right, and then m is a lower bound on your regret after m instances, then the regret has to be at least tau times this quantity here, so m divided by tau, right? So what is that basically saying? Well, we could sort of like kind of step it out, but it's very similar to the result for the perceptrons. And the worst case, the parallel algorithm isn't faster than the sequential one in this setting, okay? Now, they do have some positive results, okay, or more positive results. So this is this very clean-looking result that they have. So this is a worst-case regret, okay? So this is an adversary giving you examples, all right? So to get significantly better, then you have to hope for a little bit more. You have to sort of like say, well, there's not an adversary. Instead, these examples are coming at us IID from some distribution. So now we don't want to talk about the worst case regret. We want to talk about what's the sort of expected regret over that distribution, right? So you can say some things about the expected regret. Again, without any delay, you'll get something that looks kind of like this, right? So you have these parameters that have to do with the smoothness of the gradient and the diameter of the example space, and the regret will grow by roughly the square root of t, okay? So if we're linearly in t, it wouldn't be very interesting at all, right? That sort of means, you just make a mistake every time and that's fine, right? So square root of t, you want something sublinear. So square root of t is what you get in sort of the no regret case, all right? And then here in this analysis, the expected regret grows like this, okay? So this is sort of really the dominant term. It's the only one that depends on the number of examples, which will be, in the general case, large. And the good thing is it depends on the log of the number of examples, okay? So this is one of the results. Okay. So they also did some experiments. So these are looking on, this is a bunch of Yahoo guys. Remember when we looked at the Yahoo paper on learning on the email? I remember kind of pointing out, it's well, they tell you how much better they get, but they don't actually tell you what the error rate is, because proprietary, they don't want you to know all their details, company secrets, and so on, right? So here they actually didn't even tell us what the data set was. They just said it was real data. So it's even more kind of obscure. This is a document classification task. I could tell you what that one was. So this is the error rate when you get no delay. All right, and although you can't see it, there's another line here. Even I can't see it, even from here, but there's another line there, which is when you have a delay of 10. Okay, so this would be like sort of like 10 processors, maybe 10 threads of a machine, swapping information back and forth kind of as quickly as they can, and it doesn't seem, measurably slower, right? Okay, so the iterations are going faster, but you're getting basically the same error rate. And you start seeing noticeably slower convergence when you make that delay larger. So this is 100, and this is 1,000. Okay. And then this is like sort of the kind of like acid test, which again, it's positive, but not like super tremendously, excitingly positive, right? So what they're showing here is that you're getting a speed up. Right? This is the percent speed up, so you're getting a speed up about 4x if you use 7 threads. All right, so that's nice. Okay, to get this, they had to go in fact, in the paper, they say they sort of had negative results when they just looked at doing logistic regression this way. To get positive results, they looked at doing like an SVM sort of thing using a quadratic kernel. Okay, so this was using a kernel that involves some substantive computation. Not a lot of computation, a millisecond per example, but this is a case where, like the structured perceptron, they're doing a bit more work for each classification task. So again, this last bit, there's nothing in the quiz about this. This is really just to give you a sense for what the space of results about this process are. And sad to say, I'd like to be contradicted by this at some point. I think figuring out how much to parallelize in this sort of setting is still sort of an experimental, question and art. So iterative parameter mixing is one kind of well thought through idea. A generalization of this is this idea of delayed stochastic gradient descent, and there's a lot of work on various systems for doing that. One common approach, which I'm not going to talk about now, but we're going to talk about in a lot more depth later on in the semester, and in fact, there's a programming assignment, there's a homework assignment on this, is an approach called a parameter server. So on a parameter server, the parameters are shared, and you're actually devoting, a whole fraction of your cluster to kind of keeping those parameters around and making them available as soon as possible, right? So when you need a parameter value, you basically ask the server for it. It gives you something that's fresh. And then, the question is basically, how do you configure that? So the way you configure it, kind of the short story is, you allow a little bit of slack. So the parameter server doesn't always have everything 100% synchronized. If you try and synchronize everything completely, then you'll always be blocked waiting for the parameter server. Okay. If you don't synchronize anything at all, then you'll basically run into, You'll basically run into the setting I show you a couple of slides back, where you're getting really slow learning because you're always looking at very stale versions of the parameters. So what you're doing is you're trying to figure out how can you configure that parameter server that gives you sort of the right amount of delay so that the workers can kind of plunge forward and do their optimization, but they're not spending a lot of time waiting for each other. Okay, so I'm going to stop here. I will see you guys Tuesday. So yeah, class dismissed.